I think we'll go ahead and get started now. My name is Mike Canney. I'm with GetPackets.com. We're a Midwest company, specialized on application performance troubleshooting and application analysis. A little bit of background on myself again. I've been doing this since the late 80s and early 90s. And one of the things that kind of got me into this, right, was I can remember I started out working at IBM, analyzing OS2 LAN server on token rings, and which kind of led into some networks from a consulting perspective, looking at Arconnect packets. And one of the really cool things about network analysis, from my perspective, even back then, was I was working with this engineer that had this really cool suitcase, luggable, an old Bolt, right? Some of you remember the old pack 64s and some of the days in the DOS sniffers. And being able to take that analyzer, put it on the wire, and tell me why my customer couldn't print, right? It was back in the network, the network days, IPX, etc. So another thing that I really love about this is I'm constantly learning, right? So anybody that does this for a living or maybe on occasion, and being that we're a Wireshark, most of you probably do this more than somebody at a typical interop or something like that. It's always a learning process with applications, constantly changing, but staying the same at the same time. How many network engineers in the room? How many app developers? A couple. So hopefully I don't offend the app developers, because again, my background is networking, and you'll see kind of as a common thread throughout the presentation and some of the examples that I show. A lot of times, what I do as a consultant is defend the network. So here's the kind of a little bit of an overview of what we're going to talk about today. So to start off, talk about common issues with troubleshooting applications, leading into creating what I call a CEA, or a capture to disk appliance. Right? So building your own continuous capture machine, at a fraction of the cost, with some trade-offs, albeit we'll talk about that later. Using Pilot for what I call back-in-time troubleshooting. Right? So we'll talk about some of the ways that we can leverage that capture to disk appliance to go back in time. And what I mean by back in time is one of the most common things that I have as a network engineer, and even as a consultant, but more so when I was working for a specific company as the network engineer, was a user would call up and say, the network's slow. How many people hear that? Yeah, about everyone, right? So asking some of those, what I call detective type questions, well, what was slow, what application, can you reproduce it, those types of things. And more specifically, when did it happen? Well, it was 8 o'clock this morning. So we're going to talk about using this capture to disk appliance along with Pilot to be able to go back and look at that end user's transaction, see exactly what that user was doing at that given time, and also look at response times and what was responsible for causing that poor performance. Then we're going to get into the application QA lifecycle. Right? So we're going to talk a little bit about how applications are developed typically in most environments and why we should be concerned with that. And then hop right into what I see as a consultant. I look at about probably 1,800 applications a year. A lot of those are the same amongst companies, JD Edwards, PeopleSoft, SAP, and they have a lot of the same common problems amongst companies. But we're going to talk about those top application performance causes. And then we're going to get into one of my favorite protocols to kind of wrap up today. How many of you use SIFs? Everybody uses SIFs, right? SMB. I've got a really bad joke about SIFs, and actually, I've written just a specific one-day class troubleshooting SIFs. There's so many things, in an hour-and-a-half session here at SharkFest we can just touch on. But I have a really bad joke about this. You've heard that you can tune a piano, but you can't tune a fish. I say you can do the piano, but you can't tune the sieves. Right? So if you really want to be a nerd, we can reuse that joke. I know it's bad. We'll talk about troubleshooting sieves, some of the most common problems with it, and why it's not the protocol of choice, typically, or it shouldn't be, and how to create some Wireshark profiles to help troubleshoot that better. So, issues with troubleshooting applications, and I'm looking at this from a network perspective. Right? My background is network engineering, although I've gotten into a lot of application analysis. I'm not an app developer, I'm not a coder. I was in college, but that was many moons ago. So really, looking at application performance costs your customers, or can cost your customers, or your business money. Right? So depending on the industry you're looking at, depending on the application itself. I know in the financial industry, worked with a company out in New York that actually said that they saved $42 million in 1 month by tuning their application performance. And they've actually got a formula that says for each millisecond of delay for this trade, it's costing us X amount of money. So they've quantified the ability to say, okay, for these transactions, if we can speed this up, we can save X amount of dollars. It's not the network. I love that phrase. The network is typically, in most environments, guilty until proven innocent. So my job as a consultant, your job as a network engineer, a lot of times is probably going into these organizations and proving that it's not the network, and more importantly, pinpointing what it is. Right? So that's the key, especially as a consultant. I wouldn't have very many consulting engagements if I just went in and waved the flag and said it's not the network, because all the network engineers are doing the same thing. So what we're going to talk about is some ways to help pinpoint and exonerate the network, or again, more importantly, pinpoint what it is. User response time is what I call relative. Right? So have you ever been in this situation where user in this queue says, oh yeah, network's horrible. Boy, this thing's so slow. But the user right next to him in the same queue says, oh, yeah, it's fine. Right? So quantifying what is good, right? So if I told you that I had a response time of 900 milliseconds, what would you say? Is that good? Is that bad? Depends on the application, right? 900 milliseconds in a typical file transfer is pretty darn quick, right? Depending on the size of the file, right? But 900 milliseconds in a trading application is horribly slow, right? A 900 millisecond three-way handshake, or send act back for my first send. Something's wrong. Right? You shouldn't be waiting, especially in a LAN environment, close to 1 second for that connection to set. So again, user response time relative. This brings me to a story. I was deploying a network, and this is right around Y2K time, for a telco in Iowa. And I know there's some people in here who probably know this, so I got to make sure that we change the name to protect the innocent. So we were doing this network build-up. Right? And we had, at the time, adults. They were walking around with our TAC-64. And there was this one person in this building that constantly complains. How many people in here have that user? Right? That one user that's always calling in and complaining that things are slow. Right? And so what we would do is when we were in this building, there's always a help desk taken over for this specific user. And so we'd stop by this person's desk, plug in our analyzer, right? Say, okay, run the transaction. You sit there, watch it. Boy, everything was fine. Then we'd plug the sniffer and we'd go away, drive 30 miles to the next building, phone her, ring. Oh yeah, so-and-so had problems. We'd come back and we'd plug in. And it got to be about 3 weeks since this, user called in and complained. I'm like, wow, this is really weird, because this person calls every day, 3-4 times a day. And so we were in that building on chance, my manager and I, and we're like, let's stop by, John's desk and see how this application is performing. And we walked over there and said, hey, we haven't heard from you. Things are going pretty well. They said, yeah, the network is just screaming. Last week, Chris stopped by, and swapped out my monitor. Now everything's really fast. True story. Right? So it's relative. Right? Unless you're monitoring, and I'll harp on this a little bit later about the importance of application performance management and application performance monitoring, you don't know. And the last bullet point on here is probably one of the biggest things that I run into is reproducing the problem. Those intermittent performance problems, right? So as a network engineer, if something's broke in the network, we know about it, right? Those are the easy problems, right? Circuits down, circuits flapping, switch ports going up and down. Even in the case of some, trunk duplex matching, those mismatching, those types of things, those are the easy problems. But the moving target is what I find most often the hardest thing to troubleshoot, right? Especially if you're walking around with your laptop with your analyzer on it, you plug it in, wait for the problem to occur, the problem never occurs. Well, I had this one guy that I worked with in Florida that used to say, well, the sniffer fixed it. Right? So that was kind of the running joke, is that anytime we plug in the sniffer, we fix the problem because the problem went away. Right? So again, we'll talk about how do we troubleshoot those moving targets. And really, I look at this as analyzer placement. So do we want to run around for laptops? Do we want to run around plugging in, when a problem occurs? In the cases, well, the answer to that is depends, right? Sometimes yes. Move those analyzers where they're needed. The better problem, especially with troubleshooting application performance, in my opinion, is capture anywhere and everywhere. Right? We want to have capture points at every point of that location, especially with the distributed applications that we see everywhere today. Now, how many people see a one-tiered application these days? Very rare is it a one-tier. Client to web server, client to database. You used to see that back in the Fox Pro days, right? When you get this Visual Basic front end to a database. Those are rapidly, those applications hopefully are rapidly going away. And you've got multiple web clusters, you've got multiple databases on the back end. You may have it fronted by Citrix or terminal services. So there's a lot of moving parts, and there's a lot of places where that slowdown can occur. So if we have our analyzers everywhere, we can watch that traffic as it traverses the network. You see it leaves the client at this time, it arrives at the web server at this time, it leaves the web server, goes to the database at this time. You can follow that flow of that application transaction and pinpoint where that bottleneck is. So really, to be able to defend the network, the multiple capture points is really the best solution. Now, from a commercial analyzer perspective, right? I used to work for vendors that sold commercial analyzers. They want you to buy everywhere. But a lot of times from a feasibility perspective, budgetary perspective, unless you're a huge financial organization or a huge company that can afford that kind of thing, it's usually cost prohibitive. So what we're going to talk about is commercial versus the free capture. Right? So building your own capture disk appliance, which is what we're going to talk about primarily in the first part of this class. And what we look at here is commercial versus free. When do I want to buy the $100,000 analyzer? When do I want to use Wireshark and command line utilities? Right? And so one of the things you really have to do is define your capture strategy. You have to define the capture location. So one of the most important things is data rate. Right? So if I'm going to be capturing a core or at 10 gig speeds, I'm probably going to want to buy an analyzer. Right? And there's, pick your favorite analyzer. I'm not going to mention it by name, but there's analyzers out there that can easily keep up with 10 gig rates. And you can build your own that can keep up with that as well. But at that point, oftentimes you're going to want to have a beefy, commercially made type box to do the captures. More importantly, again, what path does the application traverse? How many times have you tried to troubleshoot an application? And this happens to me almost every time, especially with new customers. Probably if you're an internal employee and you've got your own network and you've got your own applications, you may be at the point that you understand this. But a lot of times, I'll go in as a consultant and say, can I have a network diagram? Well, you know, John was working on that, but John got pulled off the wood project, and it's about 6 months out maybe. Every time. I've gone in maybe once or twice to customers that had up-to-date, accurate network diagrams. And that was because they just had migrated from an old network to a new network, and it was, you know, brand new equipment. How many have gotten an accurate application diagram? That's even more rare, right? You know, what application, what servers are involved with this application? Well, we know it goes to this web server, right? So being able to troubleshoot an application, you got to know all points involved. And I was just talking with someone in the class here that we have a common customer, and I went in to troubleshoot a problem, and they like, it's a 3-tiered app. It turned out to be a 28-tier application. That's a lot of capture points, right? So, you know, and if you miss one of those, you could be missing where the bottleneck is. And that's really not common. My worst application that I've seen as far as distributed was 32 tiers. This was a company in Minneapolis. Again, thinking this will remain nameless, but it was 32 tiers. This single end user, business transaction, user hits enter, screen comes back, touch 32 different servers. You get into that kind of thing, it becomes pretty difficult. So the next point is, what are my goals? Right? So when we're looking again at our capture strategy, we're looking at commercial versus freeware, or low-cost ware, as I call it. What are my goals? Is it statistical information? Right? Do I want to know what's on the wire as far as application traffic? Do I want to know what my network utilization is? Do I want to know, you know, what the application performance was from the time user gets entered to the time the screen comes back? And you hear me talk about that a lot because that's how I troubleshoot. Which kind of leads into I need to capture the packet. Right? So we talk about this capture to disk appliance. Depending on how much money you want to put into building one of these boxes, you're going to have different capture rates. Right? So the box that I typically go to market with, or that I typically use, you know, the PC or the rack mountable server that I build with, that we'll be talking about here, I can usually get about 200 megabits per second. Right? That's full duplex. If I'm on a gig link and I spike up, guess what? I got packet loss. If I'm troubleshooting a problem, the end user response time issue, that's not a good thing. And I don't want to have that kind of packet loss. But if I want to know, you know, what traffic's on the wire, if I want to know, you know, what the protocol distribution is, application distribution, I don't care if I've got a few packets that are not captured. Right? So that doesn't really affect me as much as if I'm trying to troubleshoot, hey, Joe's having a problem. And I say, oh yeah, the problem is we've got retransmissions or we've got packet loss. And it's my own analyzer that's causing the packet loss, right? Or you know, giving me misinformation. So this is my capture to disk appliance on a budget. Again, I call this mine. I have to give credit to a friend of mine, Mike Canney, who I work with quite a bit. We were brainstorming on building some of these devices to, you know, to minimize our costs when troubleshooting performance problems. And one of the things that we've come up with is using dump cap. How many people use dump cap? How many people use T-Sharp? Right? I would advise using dump cap for this type of solution as opposed to T-Sharp because it uses less memory. Right? So it's a little bit more efficient, if you will. Awesome command line utility. So what I do is I use dump cap and I build a ring buffer. Right? I get a decommissioned PC or purchase a 2-spec PC. The one I'm buying right now is from a company in San Jose. They'll build it to spec. It's a 1-rack unit, half-depth box. Does everything I need it to do. It's best to have multiple links, right? Especially in the Cisco world, if you're going off the tap, you want to access it. BRDP is typically what I do. You've got to have multiple links. And then this basic batch file, really it's just a DOS batch file that initiates the capture. Now if you want to get fancy, And on my boxes I've done this, you can actually have this in the registry so that when the machine starts, it captures off of all 4 NICs that I've got in this box, and it starts writing into separate files. And my last line here, pilot. And I say this is optional, but recommended. It is not optional. I should take that out of the slide. Pilot, it is one of my favorite things to come along since I can't remember. And when I finally saw the light and discovered this unique, awesome utility, I can't say enough about it. But we'll talk about more why pilot in a minute. So this is my dump cap example. So this is my batch file that I've got running. So, yes?
So if you can invest about $1,500 on pilot, then you could also probably look at investing on a low-end application discovery tool like from Blue Coat or Riverbed, which will give you in granular detail whatever you want to do.
Yeah, so his question is if you can invest $1,500 in pilot, you can typically invest in application discovery tools, those types of things. 100% agree. But pilot is not, have you used it? It's not just an application discovery tool, although it can certainly help with that. It's my go-to analysis box. And you'll see why here in a little bit. But this batch file, what this does is, it writes this dump cap -I that says capture off the interface I. The -F says slice this to 128 bytes. The -B says write out 100 files. And -B file size to 2 million basically is going to write me out a 2 gig trace. Right? So what I've done is I put this in a batch file. I've got it in my registry, but I've got start batch file also that basically will start all 4 of my NICs and start writing trace files in this rolling buffer. So some of you may be saying, why in the world is this guy, is he off his rocker? Why is he writing 2 gig trace files? How many people have opened up a 2 gig trace file in Marshall? Hey, Jeremy. Successful. How many people have opened up a 10 gig trace file in Marshall? Your hand's not going up. How about 20? 30? 40? 50? How many people have opened up a 50 gig trace file in any protocol analyzer? Nobody. I have. I have. I've opened up a 50 gig trace file in Pilot. And if I could get some of the core developers, Gerald, to fix dump cap so that I could write to a trace file larger than 2 gigs, you would make my day.
Yeah, there are capture filters.
What's that?
There are capture filters.
Yeah, those are for the read. Who wants to filter? Who wants to filter a trace file? I have post-capture filters, right? Let my analyzer capture the data. You're absolutely right, Bill. I'm kind of picking on you, but I typically do not use capture filters. I use display filters because I don't want to miss anything. And especially with some of the stuff I do with Pilot, I want to see everything because I want to know who's using the bandwidth. I want to know what applications are using it. I want to be able to go back in time and troubleshoot anything. Now,
how long did it take you to open those files?
30 seconds.
30 seconds.
30 seconds. 30 seconds to slice through a 50 gig trace. Nobody can say that. And I've used just about every analyzer ever created, back to Synco's Net X-Ray, to Novell's Analyzer, of course the Dawson F I talked about, Shanini, you pick your favorite analyzer. I played with it at one time or used it in production. I've never seen, well, back then the 64 meg trace was big, right? Because it was using RAM there. That's a whole other story. So how does this all work together? So what we've got is we've got a directory full of these 2 gig trace files. I wish they were 50 gig trace files. But we've got this directory of 2 gig trace files. Each of these files is timestamped based on when they were written to disk. Right? So you can see this directory and you can see the time that it was written out. A user calls in and complains that, what do they complain? The network's slow, right? It's always been. So what we do is we locate that trace file based on time. and we launch it into Pilot. Now, one of the things I'm going to do here is I'm going to go into Pilot. And we're going to take a look at this. Now, Pilot, again, one of my favorite things to come along, and you're probably going to get sick of me saying this, I don't work for Riverbed, didn't work for Case. Pilot works in two modes. It works in monitoring mode, which is very cool, and it works in post-capture mode. Right? So what you're seeing here is you're seeing the NICs that are listed in my current machine. I can take these views down here and drop them on any one of these different NICs that I have in the machine, including the RP cap cards I haven't plugged in. And it's going to monitor things, and it's going to alert me when there's performance problems. Right? I can set up watches. It's a full function monitoring, and not only web monitoring. You can do URI monitoring, which we'll see some of that in post capture here. You can do voice over IP monitoring, MOS scores, wireless, right? And then I mentioned this is a sub $2,000 product. I mean, again, it's just amazing. So what I've got here is I've got a file. I've got this file called Internet. And one of the things I'm going to show you here, I'm right-clicking on it, and I'm going to say Browse to Containing Folder. Right? So here we see this trace file. We see it's 2 gigs. Right? So what I'm going to show you here, again, this user called in, complained that the network is slow. So one of the things I may want to know is, what's my throughput? So I take this bandwidth over time and I drop it on the trace. Look how fast that was. 2 gig trace. And I tell you, it's not much slower for that 50 gig trace I was talking about. So again, one of the things I can see my bits per second. I can click over here and see my bytes per second. I'm going to go ahead and stick bits. And I see where we maxed out here, right? There's my spike. And maybe, again, down here it's time correlated, right? So the time of day. And I'm going to come in and I'm going to select that spike. I'm going to highlight it. And now what I want to do is maybe I want to know who is consuming bandwidth. I can drop that right on top of that. Right? So I can see kind of this string order, as I call it, of who was talking. I'm going to close that because that's a little bit big here. One of the things I may want to know is what's consuming this spike. Was it email? Was it file? Was it SIFS file transfer? What's causing the bottleneck? Right? What's causing that big spike? And I can see again over here that the majority of this traffic is web traffic. Right? If I mouse over this thing, 99.46% of this was web traffic. Right? So again, I could come in and say, well, who in the heck is doing all this web traffic? So I can, again, I can select the time period up here again. But I'm going to say overall that web traffic, show me an IP conversation. So now my list is a little bit bigger. I can see the majority of this is this 172 box talking to the 77 box. Right. If I were connected to the network here, we could resolve these DNS names. This is a public web server. You'll see what this is here in a minute. But again, what we've done is we've come in and we've looked at that usage, we've looked at that traffic. Now, what we're going to do is something really, really cool. So you say, okay, well, it's web traffic. Well, what is it? I want to know more about what that traffic is. So I'm going to come down here and look at performance. I'm going to go to web. And I'm going to go to web user experience. And I'm going to go to web download time and rate by object. Right? So I'm going to take that view and I'm going to drop it on top of web. And what this is going to show me is all of the URIs that were being hit. Right? We can filter this down further to a specific user if I wanted to drop that on top of that connection pair. But now I can see, oh, apple.com. Right? I can see exactly what was being hit, PNGs, the packages, etc. As I scroll over here, I can look at this, time downloaded, average download time, total download time, average size, method, what was it, what was the status, so I can sort on this, and I can see any, 404, 400s, 500s, all very quickly. Now, one of the things I'm going to do here is I'm going to say, well, let's look at this, and let's sort this by size. Right, so I'll sort it by size, and double-click on it, and I can see there's the file. It's 27 megs. And this just so happens to be an iPhone pulling out a package off the iTunes store. So the next step is, well, geez, you know, who was this, right? Well, if I slide over here again, I can see that it was about 27 megs. It was a GET, bring it down as quote-unquote plain text. It took 20 seconds to download this package. Now, here's the magic. Here's the really cool, my favorite thing. Well, I got a lot of favorite things on this, but I can say send this to Wireshark. So what that does is it takes just that GET or that IPA and the packets involved in completing that GET and brings them into Wireshark. Now I can troubleshoot. So what I've done, again, I've taken a 2 gig trace file. I've looked at throughput. I've looked at what this was. I've looked at who it was. I've got the packets. Now I can get in and I can do my analysis on this. We'll talk about how to do the further analysis a little bit later. But again, so if I go back to my presentation here, think about what we just saw. From a 2 gig trace, we looked at total network throughput. We looked at what applications were consuming the bandwidth. We looked at who was responsible for it. We looked at the URIs. We drilled down to the packets of slow response time in Wireshark. And we did it in a matter of a few seconds. Now again, 50 gig, that's the biggest I've captured. That's the biggest I've analyzed in Pilot, but I don't think it's a limitation of Pilot. I suspect we could go higher, and if there's any core developers in here that have beat on it more than I have, they'd probably be able to tell you, you know, just exactly how far you can push it.
With the PCAP file or overall data set?
This is a PCAP file,
Right.
individual PCAP file.
And they do data sets up to terabytes.
Yeah, I mean, on my production capture disk appliance that I use, again, I've got a folder of about 300 2 gig files, and I can pull those all into Pilot. The thing it won't do is it won't stitch them together for me, right? And I wish we could. Now, again, somebody will say, well, you can use MergeCap. Right? Well, MergeCap, when you start getting up there at 15, 20, 30, 40, 50 gig files, I've tried it. It doesn't work very well with those large files. I suspect there's some of the same limitations that DumbCap has. I don't know. Again, I'm not a developer. So why are we focusing on the application? You know, most of us in here are network engineers, with the exception of some developers. So why the application? Why don't we focus on it? Well, again, we talked about the money you can save. But more importantly, applications are typically developed in what I call a golden environment. Right? You've got the fastest PCs, high bandwidth, low latency, they're on their own switch, they're sitting right next to each other. They develop these applications and test. They move them out on the wider network, and what happens next? Ring, 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 ring. Phone starts ringing. Oh, your network, it's horrible. As a network engineer, typically, we are the people that understand packets. We are the people that understand how data traverses. It's not this big black box, right? It's, you know, packets, there's a science behind this, right? So a lot of times, again, not only are we guilty to proven innocent in a lot of cases, but we're the only ones with the systems and tools that can say, hey, it's not only is it not a network, but it's this secret grid. Right? We can pinpoint where that problem is.
And in real life, a server is hosting multiple applications, whereas in a build environment, you're not doing that.
That's true too.
Even in systems testing, they don't do that.
That's true too. We'll talk about the QA lifecycle too, right? So, good segue. He's not working for me, by the way. That was a legit question, right? So, here's my typical QA lifecycle in most companies, right? So we've got, again, we talked about the fastest machines, dedicated servers. Here's the tests that a typical QA team does, right? I've worked with these, I've worked on these before. Your functional testing. Does it work? Right? Your regressional testing, your stress testing of the servers. Right? Each different phase, you rinse and repeat. You know, it's like a go-to statement, right? It's a loop. Functional, regression, stress. Do it again. New changes made. Can we do it? Can the server hold up to 50,000 users? The thing that's missing, oftentimes, and it's getting better, is what I call networkability testing. Right? So, can the network handle it? Not just from a stress perspective, but what's this application going to do over a T1 with 50 milliseconds of latency? Right? What's the impact going to be? What if we add 500 users? What if we add, you know, bring on a new call center with 500 phones? What's the impact of this going to be? Not just is it going to work, or are our servers going to hold up? So, again, one of the things that I'll kind of throw out here is that all QA life cycles, every company should have networkability testing. Now, I do a lot of work for have in the past, right? Done a lot of work for different companies, a specific insurance company in the Midwest. And one of the things that they do is every application, before it hits the network, it goes through the network engineering team. It goes through this performance engineering group that analyzes the networkability of every single application, and they have to approve it. If they don't approve it, it doesn't go on the network. And you know that's huge. It can be very big, especially from a network engineer's perspective of saying, okay, well, we know going into this what the response times are going to be, and we can show you. So I call this a application network assessment, an ANA. Depending on your company, if you've got performance engineering, and maybe some of you, I'm sure some of you in the room here do this, but maybe you've got a different acronym. I've heard NARA, I've heard ANAR, ANAB. But what this really boils down to in a nutshell is some of the key components of doing networkability assessments, right? So identifying business transactions. When I talk about a business transaction, I mean enter key to screen and refresh. Right? So I'm going to make a hotel reservation. I'm going to look up part number 1, 2, 3. You know, anything that the user would do, whatever those key transactions are. How many users we're going to be deployed, how often those transactions are going to be run, as well as what are the network conditions this application is going to be deployed over. So we're going to be deploying this over VSAT, you know, with 1,500 milliseconds of latency. Are we going to be deploying this over, you know, DSL? Are we going to be deploying this over T1? What's my model look like? What's my network look like? And then another key factor, simulation versus emulation. How many people know what I talk about when I talk about simulation versus emulation? Some people. Simulation, again, typically done in software. It's going to do algorithmic calculations on 500 users over this T1 with 30 milliseconds of latency. Here's what my response time is going to be. Here's what my network utilization is going to be. There's a lot of really great tools that do that. Some of the pros of simulation is very quick. Oftentimes it gives you kind of a rough number of what things are going to be like, right? You know, if we want down to the millisecond accuracy, sometimes you know that's a little bit harder to model. But the beauty of simulation is being able to do it very quickly and being able to switch between 100, 200, 300, 500 users and compare them all together in a matter of 20, 30 minutes. Network emulation is the only way to determine when an application will fail. Right? When I say the only way to determine from a network perspective when an application will fail, is that if I run this over a VSAT, for example, 1,000 milliseconds latency, maybe a 256K circuit, the application itself is going to time out. And we'll see that with the network emulator. We'll see, hey, we'll actually be sitting behind it and feel it, we'll get to the air and we'll see it. In a simulation, it's going to just say, wow, this is going to run, it's going to take 1,000 seconds for this transaction to complete, when in actuality, it will actually fail. So what I recommend for every performance engineering team, for anybody that's doing ANAs, is a combination of both. Right? That's my high recommendation if you can afford the simulation tools. That's my recommendation for both. Now, one of the things I brought with me, hopefully brought with me, I think it made a point trip. Should be in every network engineer's box. And again, I don't work for these guys. Apposite makes this little emulator, network emulator. I call it a WAN and CAN. Right? So what this thing will do is it'll actually allow you to do network emulation tests. You can dial up the packet loss, you can dial up the bandwidth, you can dial up the latency, and the thing is tiny, and it's pretty inexpensive. Absolutely love this. I use it all the time, even when I'm troubleshooting. Right? So I'll go out, we'll look at an application in a LAN environment, and I'll say, well, hey, if you guys are going to move that server, let's see what it would be like if we moved it, and they can actually feel what the end user's pain would be, right, in the case of poor performance, or actually feel how good the performance would be.
What was the name of that product?
Apposite, APP-OSIT. I'll have it down here, you can take a look at it. Yes?
How different is that from Network Nightmare?
It's in the same category. I mean, Network Nightmare, again, is an emulator. There's another WAN-EM or WAN-M, depending on how you want to pronounce it. That's an open source software-based tool. I found this to be one of the easiest to use, one of the easiest to configure, and one of the most accurate and cheap. But the Network Nightmares are nice too. I've got customers that have those as well with no complaints. So again, we're going to talk about now the top causes that I see as a consultant for application performance issues. And my first, number one on the list, right, most times countdowns, you go 10, 9, 8, 7, up to number one. I'm going to app turns first. Right? So an application turn is a command or a request response pair. I send a get, I get a reply. I send a get, I get a reply. I have request, reply, request, reply, request, reply. How many people have heard of chatty applications or have chatty applications? This is what we mean by a chatty application. The higher the application turns, the chattier that application is. Right? So why this is for each turn, each time that application traverses directions, you have to wait the full round trip delay, the latency, right, or the propagation delay between point A and point B. This is, again, one of the top reasons, if not the top reason, for an application that runs great in the LAN, you move it over the WAN, and all of a sudden, we go from a 3-second response time to a 30-second response time. It's because the application turns. It's not the bandwidth, it's not the network, it's the way the application itself is written that causes this problem. So again, the greater the number of turns, the worse the application is going to perform over WAN. I call this a latency-bound application. Right? So it is constrained by latency or propagation delay, and not a bandwidth issue. So one of the things I will mention here too is I want to give credit again to Dr. Peter Stepke, who really coined this term. He used to work, anybody remembers a company called Optimal Networks, came up with this concept, and man, it's true to life. So this is what an app turn looks like in Wireshark. So what we can see is the get go out, we see the data come back, and we see another get go out. So that pair between the request, the reply, the request is what we call a turn. Right? So this is different than TCP. This is at the application level. So application turns latency. So we're going to beat on this a little bit more. And it's fairly easy to determine the impact that app turns have. Right? So it's pretty simple math. This is back of the envelope type math. Right? So, and it holds true. So if we multiply the number of app turns by the round trip delay, so we've got 10,000 app turns times a 15 millisecond latency in our WAN, that's 500 seconds due latency. Right? Pretty simple. Ping pong back and forth, 50 milliseconds to get there, to that bit to get from point A to point B, it's going to be 500 seconds to that. Now note, this has nothing to do with the WAN bandwidth or the size of the circuit. So we could be running this over a 10 gig link, or we could be running this over a T1. Doesn't matter. That's the impact of the way the application was written.
But it has doesn't it also have a lot to do with the way TCP protocol itself works, because the application has to work over TCP in most cases?
Sometimes.
Yeah.
Sometimes. We'll talk about TCP, so hold that question because I want to come back to that. Sometimes it does have to do with the way TCP window size is configured. Although with modern PCs, and I remember you from yesterday running this, I'm just kidding. I'm not gonna, no, I'm not going there. But in some applications, it matters. In some applications, it doesn't. If I don't answer that question, ask it again. So what causes all these app turns? Why do we have, why is this an issue? Right? So here are some of the most common causes of application turns or high app turns. The size of the fetch in the database call. Right? How much data am I going after with that SQL query, that select, that prefetch? How many files are being accessed? Right? So if I pull them back in a big directory of files, big directory of little files, what file transfer protocol am I using? You'll see I'll pick on SIFs here in a little bit. So those that are haters of SIFs, stick with me because you're going to love it. Loading single images in a web page instead of using an image map. Right? So a web page, you've all seen this, has all these tiny little images. Those have to come back and forth. And a lot of times, again, HTTP 1.1, 2 concurrent connections, we're going to incur more three-way handshakes, right, with more images because we can only have 2 concurrent connections open. The number of bytes being retrieved and how they're being retrieved. And we'll go into the app. My next favorite thing to pick on is application block size. Those all cause app turns. TCP window size. I'm not going to spend a whole lot of time on this because I think most of the people at ChartFest understand what TCP window size is, but I'll give you kind of a brief explanation of it. TCP window size, the advertised receive window as I call it, is the host receive buffer. How much data can you send me? Right? How much buffer space do I have available? Large window size can sometimes help and overcome the impact of latency. And I say sometimes because we're talking about app turns. And we're talking about application block size here in a minute. So depending on the application was written, and depending on the protocol, in some cases, the advertised TCP receive window size may not have an impact at all on performance. Probably a surprise to some of you, because I know throughout the years, with all these advertisements, especially in the home PC environment, oh, Dr. TCP will speed up your internet access by X amount. Sometimes. We'll definitely get on it. TCP in-flight. How many people use the in-flight data graph in Wireshark? Just maybe 1 or 2. By the end of this class, hopefully everybody's using this regularly, right? Because this is where I see find most of the problems. So what in-flight data is the amount of unacknowledged TCP data that's on the wire at any given time. Right? So that's kind of the de facto definition of this. TCP in-flight data, or that data that's out on the wire that's unacknowledged, is limited by the following things. So TCP retransmissions, right? So if I have a retransmission, what's TCP going to do? It's going to back off. Slow start's going to happen again. That's going to impact how much data is on the wire. TCP advertised receive window, right? So if my receive window is lower than my block size, which in these days it's not ever. But when we're doing throttling, we're saying, hey, slow down, I can't keep up. When that window starts getting smaller, when that window size starts getting smaller, that's going to limit the in-flight data. And lastly, which is the biggest one, I run into this probably 9 times a week, is application block size. And we're going to spend quite a bit of time on block size, especially when we get into SIFs. The amount of TCP data, this is important to understand, the amount of TCP data in flight is never going to be bigger than my advertised TCP receive window. Right? So the amount of data that's out on the wire is never going to be higher than the receive window. Something to keep in mind. And each block of data, and again, we're talking about block size again here, must be acknowledged before any more data can be sent. Right? So this is specifically true in a lot of applications that I analyze. SIFs, SMB1, anybody that's running XP, that's going to Samba, that's going to anything but a Windows 7 to Windows 7 or Windows 7 to 2008. Each block of data has to be acknowledged before I can send any more data. Important to understand. So here's what the in-flight data looks like, right? So this is a graph, and I'll show you how I got here in a minute. But basically what this is showing me is it's showing me how much data is out of the wire. Notice one of the things that we're seeing here is we're seeing it bounce up, and we're seeing it drop back down. So this top line here is, it's kind of hard to see in this graph. This is 61,440 bytes. You're going to have to trust me on this. And I'll show you how I figured that out in a minute. That's 61,440. These little spikes here are about 4K. These spikes here are about 32K. All right, so again, you can see here's 50. And this is an SMB read bouncing all over. But that's my in-flight data. Here's a little quiz. What's wrong with this picture? Request goes out. So what's going to happen here from a TCP perspective, we're going to send out our packet train, and this little bounce diagram. So there's the data coming back. Every 2 packets being acknowledged. 200 milliseconds later, another ACK goes out. When that ACK goes out, that whole block is being acknowledged, more data gets sent, and the acknowledgements go back. What's wrong with this picture? Why is it doing this?
I think it's packet burst.
Yeah, it's got to do with packet burst, absolutely. But why do we have this 200 millisecond gap before any data is being sent? Got an odd number of packets, exactly. This is what we call a delayed acknowledgement, right? So every 2 packets are being sent. The delayed acknowledgement timer, and this happened to be Windows XP, 200 milliseconds. Oh, got an ACK for that block. I can send more data. This is so prevalent in applications today, I couldn't even tell you how many times I see this. And I see this in commercial applications. Right? I see this with, I saw this with SQL 2000. That's kind of a little bit old. SQL 2000. This was the default behavior. I'm not sure exactly which version of IIS. This was the default behavior. It gave us an odd number of block size, or a lot of times the application will call this buffer size. Odd number of buffer size, you know, the 1460 bytes, again, that's your MSS, that's what you're sending for data. This happens all the time. So what happens here is each application turn not only waits that round trip delay, but also waits another 200 milliseconds per application turn for that delayed acknowledgement, all due to application block size. So this happened in a customer mine in Chicago. Right? We called out to troubleshoot this new deployment of an IIS application. Oh my gosh, it was so slow when they moved it off the LAN. You know, they deployed it to multiple locations throughout the country, throughout the world actually, in a horrible performance.
So what do you mean by application block size? Can you explain?
Yeah, so what happens is the application hands down to TCP a block, right? And in this case, if we hand down, let's say, I think I was using 1640 bytes. This is the block that I'm sending to TCP. TCP said it goes out and gets it, right? Hands it back up to the application. Well, what happened in this case is that for some of these specific applications, no data can be sent. And this is how SMB and SIPs work. No data can be sent until that block has been acknowledged. So if I'm sending you a 50 meg file, I'm going to send it to you in chunks, right? Which we call application block size. I'll send you a chunk of 16K. You have to acknowledge to me that you received that entire block before I can send any more data. So when we go back to this picture here, that's why we're seeing this delayed acknowledgement right here, right? Because we've got an odd number of packets. So a lot of these applications that are being developed, they don't know about this, right? Or don't, you know, they have control over this, but they're sending out odd numbers, which in turn, again, without selective acknowledgement and some of the other things turned on, you're going to get these delayed acts. So one of the things, again, I always do when I'm analyzing applications, I look for patterns. This is a pretty easy pattern to see. In that in-flight data graph that I showed you before, you'll see data go out, drop down 200 milliseconds, and you go out, drop down 200 milliseconds. You know, it's a very easy pattern to recognize. So here's the impact of this, right? So we've got a typical application block size of 500 app times. You got 500 times 50 milliseconds of WAN delay, plus 500 times 200 milliseconds for each delayed app return. 125 seconds or 2 minutes due to application block size, which is easily configurable. So this application I was talking about in Chicago, guess how long this took me to fix? 15 seconds. Call up the developer, call up the sysadmin, say, hey, change the buffer size, and change it to this. Problem away. This is so common. I see it all the time. Again, what I call latency bound application. So, talking about block size, we're talking about latency. Here's a little quiz, and I know this is probably going to be hard on a calculator, right? We've got application block size of 14,600 bytes. We've got a round trip delay of 40 milliseconds. What's the maximum throughput we will ever see? Now, I'm talking about throughput of this application. What didn't I mention? I didn't mention MTU, right? But the big thing I didn't mention was bandwidth, right? A lot of times when we talk about throughput, what's the bandwidth? Is this a DS3? Is this a 256K circuit? Is this a... I'm not talking about that. I'm talking about the maximum we will ever see with a block size of 1460 bytes, or 14,600 bytes, and a round trip delay of 40 milliseconds. Due to time, I'm not going to make you quiz this, but something to think about. So how we can calculate throughput is block size divided by round trip delay. So if we look at the math here, the throughput of this, we've got 14,600 divided by 0.04, that's my latency, times 8, you can do the conversion. 2,920,000 bits per second. So what are we looking at? 2.9 megabits per second? Doing that right? It's been a long day. That's the maximum throughput we're ever going to see. I don't care if you give me a DS3, I don't care if you give me a 100 gig circuit, you know. That's it. Because the application is throttling the throughput. My offered load onto that network is going to be 1460. I got to incur that full round trip time. Something to think about, right? So that's horrible. So we don't want block size. We don't want, you know, single-threaded applications.
Or would you change that application block size? Is it something the developer has to do?
Yeah, so his question is, where would you change the application block size? Is it something the developer would have to do? It depends. 90% of the time, the developer can change this, depending on the application. Sometimes you can't. Sometimes you're stuck. Sometimes it's a rewrite. Sometimes, with the case of SIFs, SMB version 1, there's not a dang thing you can do about it. Right? You are stuck with the way that it's implemented.
Well, for instance, you said there was an application on IIS. Are you changing the application block size for IIS? Or?
Yeah, the block size was for, in that case, was for IIS. They called it a send buffer. And we just increased the send buffer. So here's a cool little bit of homework for you. How many people use, what is Mozilla's FTP server? FileZilla is the client. FileZilla server? Okay. FileZilla, you can go and you can change the application block size. And for one of my classes, again, for one of the app analysis classes, I've customized this. I've changed it to like a odd number 3K block size so that it takes 3 packets. And you can see this all day long. I mean, if you want to test this for yourself and you want to use either, you know, one of these, you know, inexpensive WAN emulators or go download WAN EM, you can do this. You can say, okay, let me tweak the block size and let's see what the impact is. And you can do this for SIF. Well, you can't tweak SIFs, but yeah, that's a good one to do some testing on to see the different improvements. And a lot of times I've run into FTP issues where they had that buffer size set way too low, and that was the problem. And it was, again, 15-second fix on the FTP server.
I have a couple comments actually. I've encountered this very same scenario. I work quite a bit with everything from command line FTP clients to databases, very frequently databases actually. And I just want to make the point that we want to increase the buffer size such that the TCP windowing mechanism becomes a primary flow control mechanism. You don't want to try and make it an even multiple of your maximum segment size.
That's a good point. You know, one of the things too with you know, most people, if they're not, they should be using Windows scaling, right? So a lot of times, even with scaling, it's going to be a block size or it's going to be a latency issue. You know, again, depending on the application. So a lot of times, hopefully, most of the database traffic stays local. I mean, I've seen applications where they moved a database to a remote location from the app server, from the client, you know, separated by latency. You know, majority of the slow applications I see, you know, app to web to database, it's again, I apologize for any DBAs in the room, but 90% of the time it's the database. You know, or poorly written call to the database, even in the LAN environment. But yeah, that's a good point.
The other thing I wanted to mention is that you can change the registry setting for SMB block size, but only up to 64K.
Yeah, so yeah, 60, that's, yeah. The problem is still with SMB reads, even if you change the registry size, you're still going to get it bouncing all over the place. 61,440 for an SMB write is typically what you'll see, but you can bump that up. And for some reason, the write, and I've talked to people at Microsoft about this, so why the difference? We'll get to that in a little bit here. So the next piece here is TCP retransmissions. So every time a TCP segment is sent, a retransmission timer is started. Right? When the acknowledgement for that segment is received, the timer stops. Pretty basic. If the retransmission timer expires before the ACK comes back, that TCP segment is going to be retransmitted. Excessive TCP retransmissions, again, not a big surprise to probably most of the people in the room, can have a huge impact on app performance. If I'm dropping packets, if I'm retransmitting, my retransmission timer is too low, which doesn't really happen much anymore, but it used to in Windows 4 days, or NT4, could have a huge impact. Not only does it have to get resent, but you got slow start, everything kind of starts over, kicks in the action, like a chain. Troubleshooting CIFS and SMB. I'm going to say boldly that it's arguably one of the most common file transfer methods, file transfer protocols, if you will, used in business today, just because of the prevalence of Microsoft. Right? You know, there's a lot of FTP out there. There's a lot of other means of file transfers. But I run into SMB. Everybody in here is running it, most likely. And it's also one of the most chatty. If you look at the historical nature of SMB, you know, development Big Three, you know, back in the day, it was not developed with the WAN in mind. Right? So the LAN protocol started out kind of in that buoy days. And it's one of the most chatty. There is no RFC for SMB. Right? There is no standard for SMB for the most part. You know, some documentations. And there's hundreds of dialects, hundreds of different implementations of it. Not the real reason that it's as poor as it is, but really, you know, one of the most chatty applications I run into, again, with the exception of poorly written SQL. And this is probably one of the things I run into the most from a troubleshooting perspective. So here's a little quiz, and maybe from some of the stuff you probably figured this out already. But what's faster in a Microsoft file sharing or an SMB file sharing situation? Pushing a file to the server or pulling it from the server? And I was in one class. I was in one class where a real bit twiddler was in it, and his answer was it depends depends on the elevation of the server, because we all know packets flow faster downhill.
Wonderful.
No, not the elevation. You would think it'd be the same, right? You would think pushing it, pulling it, doesn't matter. Brings me to a story. Working with a client who was doing nightly backups across the DS3. And they were going from Des Moines, Iowa, down to some obscure data center in Florida. Right? They were backing this data up nightly, pushing the data down to the server, pulling the data from the data center. And so in this case, initially, they were actually pulling the data. And so they had written a script that would go out, go to the database, or go to the data store and pull that data. It was taking them close to 24 hours. You come in the next morning, things still running. They go home that night, things still running. Almost 24 hours for that file copy to happen. Said, well, let's try pushing it instead of pulling. Cut the time in half. And then we used another UDP type file transfer, which we can talk about after class. If anybody has questions on that, cut that down to right around an hour. So they went from roughly 24 hours, cut it in half, down to an hour. All because of a push or pull. And what this boils down to, again, is block size. Right? So what I'm going to do is I'm going to show you just kind of a basic SMB pull. Right? And what I'm going to show you, kind of like a cookie machine, is there's man flight data of a file that you can see here that I basically did an SMB read, pulling it off the file. See how we bounce up and down? 4K, 31K, 61,440. And it took roughly 60 seconds, a minute, for this file copy to happen. This was in a clean, pristine environment, using my WAN emulator, no packet loss. I think I was doing a 3 meg circuit with 30 milliseconds of latency. Just a typical bonded T1 environment. Here's what happened when I did an SMB write. There's the trace file. Notice the difference?
Good.
All 61,440. You don't see any of those little 4K, 32K. The SMB read is all over the board. I mean, you can push that up, like the gentleman said with the registry change, but it's all over the board. The SMB write is constantly 61,440 bytes. Anyone in here from Microsoft? Nobody? Nobody can explain this to me. Why is the read different than the write? And again, probably because there's no RFC, there's no real documentation for SMB. But one of the things again we can see is this same file took half the time, 30 seconds. Same network conditions, pushing it versus pulling it. And so, one of the things that I've done is build some stuff to help you. Now, I want to show you this, right? Let's talk about SMB2. How many people in your organization are running Windows 7 and Windows 2000 servers? How many people that raise your hand? There's only a few of you have SMB2 turned off because of security reasons. Nobody? Good, because there's no security problems anymore to worry about that. Here is my SMB. I can't type this off at the same time. Here's the IO graph for SMB2. Now this is a different file, so don't compare the transit times. Well, look at what we're doing. I've got Windows scaling turned on here. I'm pushing 250,000 bytes in flight versus my 61,440. Just think how much faster this is going to complete compared to SMB1.
But that's not just window scaling, that's because SMBV2 allows batch pushes.
Yeah, so this has window scaling. The other machines had window scaling turned on as well. But it wasn't TCP that was bottlenecking. It was the application. And so that's the important thing to take away from this, is that we had scaling turned on all three of those trace spots. But it didn't matter what the advertised receive window was. The application was handing down 4K and say, hey, go get me 4K. Well, we had to traverse the latency. We had that extra application turn for that specific latency. So SMB2's got a number of features that are much better than its predecessor. So number one, we don't have a fixed application block size. It's basically, it's much larger, let's say it's 64K, but it's multi-threaded. So I can have multiple gets, I can have multiple reads, multiple writes going on at the same time. Much more efficient. Now, what I've also done for troubleshooting purposes is I built a profile right there. I built a profile here for troubleshooting SMB. And you can see right now I'm looking at my default profile. This is just a regular file transfer. This is, I think, an SMB write. Now, one of the cool things I can do is, again, cooking show style here, because of time. There's my SMB profile, right? So what I've done is there's a lot of really cool things, a lot of really cool calculations that Wireshark will do and allow you to build out specific columns for these. And one of those is SMB byte count. So I can see how much SMB traffic is being sent. I can also see SMB time, which is really, this is awesome for troubleshooting server response time issues, right? So I can see time from request for that SMB transaction. So for that read, for that write, for that trans to, for any of those different SMB commands it creates, I can see how long those took. And again, when we highlight over that, we can see what that is, SMB.time. I've got SMB command, I've got TCP window size, and I've got file data, right? So I can see what this user is sending. Are they sending a PowerPoint? Are they sending, what are they sending? What is this transaction? Now, to make this kind of better, and I left in some of these other things in SMB bytes and the other standard source destination. You can arrange these any way you want, really. One of the things I like to do is I like to come in here and type in SMB, not CMD, and apply this. So what this is going to show me is all of my SMB, it's going to filter out everything else but my SMB commands. And again, going back to application terms, we can see that displayed here, we've got only SMB commands. We've got request response sequences. I've got 353 app terms in this. So I can look at this transaction and I can tell you how many turns this has. And if I knew what the latency of this circuit was, I could tell you how much of this overall 30-second file transfer was due to latency. How much it was due to bandwidth, how much was due to latency, some of the key things you want to figure out. So how did those 353 app turns affect me? Now, one of the other really cool things I can do with this too is I can export any of this data out to CSV. Right? So what I'm going to do, I don't have my CSV cooking show style. What I'm going to do is go over here. Actually, minimize this. Go to my open office. And load my spreadsheet here. So what I've done here, actually, is I've exported my profile, or that information out of my profile. You kind of see it kind of back behind the track. You kind of see what I've exported out here. Right, check directory and the SMB cumulative time. So now what I can do is I can look at this trace file, I can look at this file transfer, and I can tell you where my bottleneck is within the protocol. How much of that's due to, and you can see here from a time perspective, This NT trans summary is what's killing us. Right? So out of this 32-second or whatever it's happened to be from a file transfer perspective, we can see how much that was actually writing. In this case, very little for this trace file. And this, this changes depending on what you've got. But again, very powerful things you can do if you use the export feature on a Wireshark and graph it in, open Office, Excel, whatever you have to use for a spreadsheet application, and you can include this into a customer report, right? And you can do the same kind of things for HTTP, web transactions, etc. And again, a lot of the HTTP stuff, the old Pilot, which I recommend everybody owns, you can do a lot of really cool reporting out of there. The only kind of drawback that I see with Pilot with this is that it doesn't really support or have a lot of information for SMB, so you have to kind of get down into Wireshark and you have to kind of export this type of stuff out. But, we'll stop. So here is my personal SMB profile. That is what, from a columns perspective, right? This is just a column side profile. This is what I've got in it, right? So we've got the frame number, the time, the bytes, SMB byte count. I'm not going to read this to you. But you can see this. These slides will be available, by the way, up on the Case or Riverbed site, SharkNest site. So you can go out and download those if you're interested in what I use for my personal SMB profile. Any questions?